So today we will start chapter 2. So you see the syllabus. Do you have that? Chapter 2 starts with deals with electrostatic potential and capacity.
Yeah.
Okay. Electrostatic potential and capacitance. Chapter 1 was all about electric field, electric charges. This one is about electric potentials. So now electric field, see, we discussed about electric field, right?
Yeah.
And I gave you the analogy of magnets and like that. So electric field are the regions where we can experience the force. Okay, the force produced. So if this is some charge Q, this is the type. This is the electric field of a point charge, right? It
Yeah.
is radially outwards, spherically symmetric. So at any point inside this field, another charge would experience a force, right?
Yeah.
That is what an electric field is. Like anything put, any charge put into the electric field, that would experience some force,
Yeah.
be depending on the polarity of charge. So there is another way to define electric field. That is by using electric potential. All right.
Okay.
Electric field is a vector quantity. We already know, but electric potential, in contrast, it is a scalar quantity.
Yeah.
It is not a vector. Now let us see what is electric potential. So for that, let us see first what is a potential difference. Potential difference. So in order to do that, let us consider a point charge plus q, okay, situated at some point. There is some charge plus q situated at this point, and let there be 2 points A and B in the vicinity of this electric field. Okay,
Okay.
so let there be a point B, and there be a point A here also, and we know that both these points should lie in the electric field due to this q. All right.
Yeah.
Now we bring a test charge q naught. We have a test charge at this point A, and we want to bring it from A to B. We want to take it from A to B. Now, because since there is an influence of electric field due to this charge, right?
Yeah.
So the movement will take some amount of work, because there is this electric field that would be pushing this charge away, isn't it? The force on
Yeah.
this test charge due to the electric field of this charge would be away, right? We want to bring it closer, we want to bring it to the point B. So there is an electric field influence, and when there is an electric field influence, that would not, we will have to do some additional work to move it from A to B.
Okay.
We cannot simply move it from A to B now. This is the same that as a magnet. If you have a magnet,
Yeah.
it's south north, you want to bring it another magnet which is north south close to it. It will not move on its own. You have to do some work, right? It
Yes.
tends to throw it away, isn't it?
Yeah. Yeah.
The same is the case here. Due to the influence of the electric field of this charge q, we will have to do some work in moving this charge, test charge, from A to B. And let's say that that work is WAB. Okay,
Yeah.
so WAB has to be the work done against the repulsive force of Q. Then the potential difference between A and B is, so we call it as VB minus VA. Let's call it V, which is equal to work done divided by the charge that we want to move. Okay, this is the potential difference between points A and B. Let us let us recall this. Let us recall this. There is charge q, okay, and in the vicinity of this charge, there are 2 points A and B. We want to move this test charge from A to B.
Yeah.
So this will repel
Yes.
this, right? We need to do some work,
Yes.
and that work is WAB. Okay.
Yeah.
Now the potential difference between A and B will be defined by that work done, okay, WAB, divided by the charge.
Okay.
That's what potential difference is. Okay.
Yeah.
This V is also called VB minus VA. Okay, the potential difference of V minus potential difference of A is given by work done upon charge. So potential difference, let us write the definition. uh, with another pen. So potential difference between 2 points is what? It is the amount of work done in moving, so it is the amount of work done in moving a unit. This is a unit charge, okay? We will assume the unit charge from a point, from a from one point to another, that is from A to B. So from one point to another inside the electric field, and against electrostatic forces. This is what potential difference means. So this is a point B, this is point A. If there were no electric field, VB will be equal to VA. Alright?
Yeah.
But since, see, there would be difference in electric field due to Q at this point and at this point, right?
Yeah.
That's why we have different potentials. Okay?
Yeah.
So this is another way to define this electric field. You should remember this, the formula. Okay, potential difference is the work done in moving. See, you can correlate this. This is VB and VA, and this is WAB. So the potential difference is the amount of work done in moving some charge, unit charge, from A to B, right?
Yeah.
Divided by that charge. Now let us see what is the definition of what is the SI unit. Sorry. So you can see this is work, this is charge, right?
Yeah.
So what is the SI unit of work? Joules.
Joules.
And what is the SI unit of charge? Coulomb. So
Coulomb.
that would be joule per coulomb, the unit of potential difference. And it is
Okay.
given a special name in the honor of the scientist, which is called volt. Okay, so both of these are correct, although it is seldomly used. Volt is the more used SI unit. Now this is the potential difference. Now let's move again to this thing. We want to find what is electric potential. Okay, this is the potential
Yeah.
difference. We want to find the absolute potential of a point.
Okay.
Suppose you want to find VB. Okay, in that case we need to find its electric potential, not the potential difference. Potential difference is between the 2 points,
Yeah.
but if you want to find the potential of this one point VB, okay, how do we do that? So if you see the same figure, okay,
Okay.
in the figure above, what happens if a the point A is at infinity? If this point is at
Yeah.
infinity, okay,
Yes.
then we can we say that VA, the potential at A would be 0? See, there is some potential when there is an electric field, because they are
Yeah.
two related. This charge has an electric field, but if we move this point A to infinity, then that would no longer be under the influence
Yes.
of this charge. So we can
So it will
safely
be
say
0.
that if A is moved to infinity, then VA would be 0,
Yes.
right? Now in this, can we now say that this thing, so if we put this as 0, what would be V? So we will have VB only here, right?
Yeah.
And is equal to V is equal to WAB divided by Q. Okay,
Yeah.
but this is not WAB now, because we are not moving from A to B, we are moving from
Yeah.
infinity to B, right?
Yeah.
Or you can just say it infinity to B divided by Q naught. Okay,
Yeah.
so now what have you got from this? See, VA has been moved to infinity, only VB now remains.
Yes.
And what is this WAB? Sorry, W
What?
infinity to B? The amount of work done in moving a test charge from infinity to the point B.
Yeah.
So the definition goes itself, right? We have found VB. Okay,
Yeah.
what is VB? VB is the potential difference of point B, and it is the amount of work done in moving a charge from infinity to point B.
Yes.
So electric potential definition goes like this: it is the amount of work done in moving a charge from infinity
Infinity.
to that point. Okay,
Yeah.
so that is the absolute potential of the when we move from this point from infinity, then that would give us the absolute potential of V, because that will be 0, isn't it?
Yeah.
According to formula, we will get this thing. VB is equal to this W upon Q. Now let us see what is the potential due to a point charge. We studied the potential due to the electric field due to a point charge, right?
Yeah.
Let us see what will be the potential due to a point charge. Electric potential due to a point charge.
Can I be back in 1 minute?
Yeah. Uh, see this diagram. Here we have a point charge Q situated at a point O. Okay, this is the Q charge. We want to find the electric field at this point P, or not the electric field, electric potential at this point P at a distance R from this. Okay, now for that what we have done is we have chosen 2 points, this A and B. Okay, and this point A is at a distance x from the charge Q. Okay,
Yeah.
and there is this point B. Now first tell, suppose this is the test charge Q naught placed at this point A. What would be the force acting on this charge? This will be the force in this direction because they both are positive.
Yeah.
What would that be? 1/4 pi epsilon naught Q naught
Q naught upon R squared.
divided by R square, but here it is x,
So X squared.
so we should write x, isn't it? Now this charge Q naught is being thrown outwards, right?
Yeah.
This force is acting outwards. Now
Yes.
the small work is done in moving the test charge from A to B, because the distance from B to A we have assumed as dx, right? This is the small distance dx. This whole from A to 0 O to A is x. Suppose we need to push it to B, like the small distance, right?
Yeah.
So
dx.
correspondingly there would be small work required
Yes.
to move it from A to B, isn't it?
Yeah.
And what that work would be? dw. Okay, and if you know from class 11th, you know what is given, what is the definition of work? F dot ds.
Huh?
Okay,
Okay.
this is the formula for work, for dot product of force and displacement, right? So we can find dw as F dot dx.
Yes.
This is from class 11, this is the formula for work. Okay,
Yeah.
now this dx is in from A to B direction, right?
Yeah.
And this force is in the opposite direction, so there is a 180-degree angle. So what would the dot product be then?
F modulus X.
F dx cos theta. Theta is 180, cos 180 is
So-
-1, isn't it?
Minus. Yeah. So minus.
So this is -1. What we get? F dx, right?
Won't it be minus?
Oh, sorry, this would be minus here. This is the small work done in moving this test charge from A to B, right? But we want to find the potential at this point P, so we want to move it from infinity to this point P,
Yeah.
right? So how will we find the total work done?
Um, what the
See, we
previous
have
one
moved it a
was.
small distance. We want to move it up till here. So can we add each one of these small dw
Oh, like multiply by 2.
and reach P? No, this is not equal.
Okay,
This is a
my
small
bad.
distance. This is just for illustration purpose. This is a small distance dx. This may be like this. This is P.
Yeah.
This is B. This is A. This is very small. You need to move to this point, no? So we
Yeah.
can add each one of those small works and then move at P.
Yeah.
Okay, because this is a small work done. So that would be the whole work done, right?
Yeah.
And how do we find that? Integral of dw. Okay, integral of dw, isn't it?
Yes.
From infinity, we want to move it
2.
to R,
Yeah.
to point R. These are called the limits of integrals. Okay, we need to move
Yeah.
from infinity to R. Now what is dw? You can replace this with minus f dx. Okay,
Yeah.
and this is what f is. We already found 1 by 4 pi epsilon naught you getting it, q naught
Yes.
upon x squared dx. Now let us take out the constant terms. So this is constant 1 by 4 pi epsilon naught
Yeah. So, yeah.
q naught divided by x squared dx. See, 1 by x squared dx is not constant,
A constant.
it is a variable. So we will keep it here inside the integral.
Yeah.
Now further, q naught negative of this. Now you can write it as x to the power minus 2 dx. Okay,
Yeah.
and if you know, you might also know this. What is the formula for integral of x to the power n? P.
No, I don't know.
There is this formula. The formula for
Wait,
what?
I never learned.
Yeah, you have not
Uh,
learned this. You have not learned this, but this is uh, given in class 11th and 12th books. It's in the start.
okay. Because it came up in chemistry also. I was so confused.
Where it came?
Chemistry.
Actually, the thing is, see, they are in class 11th. It is told as an introductory part.
Oh,
But the thing is, it you will study it in class 12th. Integral is not in class 11, but it is told to just to know. Okay.
okay. Because and then the other day I was learning chemistry and then something like log came up.
You will find those formulas at the end or at the start of the physics book.
Yeah. Okay.
Integral formulas and all the derivative formulas. Okay,
Yeah.
I'll tell you how we do this. That's elaborative part is in class 12th, but as of now you need to learn the formulas directly. So this is the formula of integral of this, whereas n is a n should be an integer here. Okay, x to the power n plus 1 divided by n plus 1. So let's apply that here. X to the power minus 2. So minus 2 plus 1 would be minus 1. upon minus 2 plus 1, again minus 1, and the limit going from minus infinity to r. Oh, that's plus infinity. So this minus gets cancelled. Okay, so q naught upon 4 pi epsilon naught. This is 1 by x to the power minus 1. Now if you solve this, you need to, now there is how do you solve this? You need to substitute the limits. And how do you substitute the limits? Suppose we are given x from a to b. Okay,
Yeah.
so what we do is we substitute a in place of x, so a, and then we put a minus sign, and then we put b in place of x, so b. That is how we find it. So here also we will substitute r in place of x, so 1 by r minus 1 by infinity,
Yeah.
and 1 by infinity is 0. Okay,
Yeah.
so 1 by 4 pi epsilon naught q naught by r. Okay,
Okay.
this is the final result. Now what is this? This is the work done. Remember, this is the work done. We have not found the potential.
Oh, right. Oops. Yeah. Okay.
This is the work done, and corresponding to the work done, how do we find the potential? P is given by W upon Q.
Yes.
Q is that charge, the test charge.
Yeah.
W is 1 by 4 pi epsilon naught q naught by r. What is our test charge?
Q.
Q naught.
Yeah.
Test charge is Q naught, not Q. Q is the fixed charge.
Yeah.
So Q naught. So this will get cancelled.
Cancel.
And V is 1 by 4 pi epsilon naught Q by R. This is the formula for potential, electric potential due to a point charge at a distance of r from it. So as you can see, this V is inversely proportional to R, right?
Yeah.
And the electric field was proportional to the 1 by R square, isn't it?
Yes.
So it will diminish very fast. It will diminish still, but slowly. Okay,
Yeah.
like the curve would be steep for this electric
Yeah.
field, as you can see in the figure in the book as well.
Yeah.
Okay,
Yeah.
now this is also spherically symmetric. Okay,
Yeah. What? Can you explain what that means? Spherically symmetric.
I like, it's the same thing, no? If suppose if you have a charge, it would be same at all points on the
Right.
sphere.
Okay. Got it.
That's what spherical symmetric means. Okay,
Yeah.
there is cylindrical symmetric also. Cylindrically symmetric means at all points on the curved surface area of the cylinder, something can be the same. Okay, we will also study this. Okay,
Yeah.
this will get in midway while we study electric field due to dipole, electric potential due to dipole. So I think that's it for today. Okay.
Okay, I didn't try any of it.
What?